Alright, chapter 11, when I do this, even in face-to-face classes, when I do this, I don't really go through it and make you do a lot of grinding of computations. More at this point, I try to make sure you understand an overview of how what we've learned, particularly in chapter 9, relates to things in real life, how they determine what's causing cancer, what's, whether masks work or not, and things like that. And so, for those tests, and whether a vaccine is going to work or not, they give one group the vaccine, and they'll have one group as a control group, and they'll compare the results and see the rates of which people get a virus or some sort of condition. You know what I'm talking about. But anyway, so that means we got to compare two separate samples, the control group and the treatment group. And so it's very often that they'll be doing two population studies. And you don't have to take any notes because I'm not going to test you on this other than just making sure you understand how these work. I'm going to skip to 11.2 first, and then I'm going to kind of bounce around. So I'm going to do 11.2, an example, and show you on the calculator how this would work. And then 11.1, I'm going to backtrack and do 11.1, and then I'll do 11.3. And this shouldn't take more than half, I don't want to say, but it's going to be short because we're not going to grind out any kind of computations. They're much more difficult than we can really deal with by hand, so we're going to rely on the calculator. All right, to illustrate 11.2, which is independent samples, that means there are just two groups that are completely independent of one another, and we'll do that by testing the question if women have a higher IQ than men. I don't want to suggest anybody's claimed that, but let's just test it. All right, and they'll oftentimes, when they teach you this, they'll have just group 1, group 2, sample 1, sample 2, and it's important you keep track of which one is which and which one you think, or your alternative, which one is higher than the other. So women are going to be group 1, men are going to be group 2. Your null is that they're equal, that the average, and these are average IQs, the average IQ of all men is equal to the average IQ of all women, and that's our null. We just default to that. Unless we have evidence that women are actually more intelligent than men, and we need to prove it if we're going to make that claim. And to prove it, we're going to be doing a test and seeing if we reject that via a small p-value, and we can conclude that the average IQ of group 1, women, is actually greater than the average IQ of group 2, the men. And we don't have access to the IQs of everybody, all the men and women in the world, so we're going to have to base our conclusions on just a random sample of men and women. And you hope they're good representatives of each group. But here we gather these, and I'm keeping it small samples. You wouldn't do a test with only 4 women and 5 men. You do like 20 at least, and possibly hundreds if you had the time and money. But for simplicity's sake, and so we can actually enter it on our calculator in a reasonable amount of time, let's say we have a sample of 4 women and a sample of 5 men. Now the order of these doesn't matter. This woman is not married to that man. They're just sort of in a random order. And that's the important thing to know. They're not paired up in any way. It's just a separate group of 4 women and a separate group of 5 men who probably don't even know each other. That's where the independent comes from. That's going to be in contrast to what are called paired samples, but we'll get to that. Anyway, average IQ of the women, these 4 women is 108.3. Average of the 5 men is 105.2. The average of these women are slightly higher than the average of these men of this random sample, but it could just be the random nature of the draw. Standard deviations, sample standard deviations are similar but different. We'll talk about how that's relevant. And anyway, what you're doing for this test, and we're not going to do it, technically the formula is it's a t-test. It's going to be what's called a 2-sample t-test. But the test statistic for any test is going to be a t1. And it's complicated. It's going to be looking at that difference between x bar 1 and x bar 2. It'll be looking at the difference between 108.3 and 105.2. If it's a big enough difference, we might conclude women are actually smarter than men, and if it's only slightly, a slight difference, a small difference, we probably default to, nah, it doesn't look like there's any difference, any statistically significant difference. We feel it'd be close enough, depending on the p-value, what our p-value is, and to get there we need to grind out some numbers, not by hand, because at this point your computations are so intense that nobody ever does it by hand. So at this point we'll default to using software. I'll do it on my calculator on the screen, and I'll also show you on StatCrunch so you can at least see what you missed out on via labs. Just using software It's a very cheap, basic software compared to some of the more expensive ones, but we'll work it out in there. I will mention if you ever take this class somewhere else, not this class, but a higher level stats, and you're doing this test, one of the distinctions you have to make is between pooled or non-pooled, and that's why there's two separate formulas. The idea is, well, first of all, we're using T because you use T, I mentioned it before, when you are using sample standard deviations to estimate unknown population standard deviations. So it would be great if we knew sigma, the standard deviation of the IQs of all women and all men, but we don't. All we have to go on are the samples. So we are using S to estimate sigma. We're using S1 to estimate the standard deviation of all women. We're using S2 right here to estimate the standard deviation of all men. And that estimation, using that as an estimate, means greater uncertainty, which means the probabilities have to be tweaked via using T instead of Z. Now, if you think the standard deviations of men and women are the same, you can basically take these two standard deviations in all the data and group them all together. So pooled means, for the purposes of standard deviation, you're just going to assume these are together and all the standard deviation, we can treat it as one group, and you kind of combine the standard deviations by taking your S1 and S2 and doing what's called a pooled standard deviation. If you don't think that, if you think the standard deviation of men and women might be different, then you have to keep it separate and you would be doing a non-pooled. As far as making that call, it pretty much your instructor or the textbook you're using should just tell you which one you're going to do. It's not something you would be required to make a call on. I wouldn't be comfortable doing it. So usually they just say, okay, we're always going to be doing pools for this chapter and in this course. All right, anyway, I'm going to do it on my calculator, but I actually have it in this data here. And I'm going to be doing a test on here and spitting out a p-value. I can get the t statistic. So again, you're going to do one of those computations, either pooled or non-pooled. And I think I did pooled. I'm going to be doing pooled. That's pretty standard, is at this level they just default to pooled sometimes. And I'll be getting a t. I'll be using the t distribution with this degrees of freedom, n1 plus n2 minus 2, so it's going to be 4 plus 5 minus 2, so it's going to be 7 degrees of freedom. And we'll get a p-value out of it. So we'll get a t and a p-value, not by doing hand computations, but by getting the whole process to be done via software. Okay, so I put my data in L1 and L2. It is important for these to keep track of, again, which one is the women and which one is the men, because we were testing if women, group 1, is higher than men, and so the direction right-tailed, left-tailed, or two-tailed matters. I'm going to just do this and I'll show you what I'm doing on the screen. 2 sample t-test is what we're doing. Okay, and I'm going to do pooled. And if you do non-pooled instead, the answers here are slightly different, but they usually don't make a difference. So it's oftentimes not crucial that you really make the correct call on that. I'll do pooled. As I said, that's usually the default at this stage. And let me see. I got a t of 0.329 and a p-value of 0.376. Okay, and your standard, I didn't write the significance level down, but for these kinds of tests, it's 5%. Every test in medical study, vaccine study, any kind of thing like that, we'll be looking at 5% as your significance level. So our p-value is nowhere near below the cutoff. And now you have to remember what that means. So we're going to draw our conclusion here. Based on this data, these 4 men and 4 women, our conclusion is to not reject the null. So we're not rejecting the null, meaning we're ultimately accepting it. We're accepting the fact that there is no difference, that the average IQ of men and the average IQ of women are not significantly different. So, and I'm going to start using different phrasing that's more in line with what you'll see in real life. No statistics, what am I writing? There's no statistically significant, that's referring to the significance level. There was a slight difference, but it was not below the significance level, and that term significance comes up as statistically significant difference between the IQs of men and women. Okay, and this data is completely made up. That's not real life data, but the result is real. There's been no evidence that there is a difference between the IQs or intelligence of men or women. So, yep, everything's fair. And let me go ahead and show you the well, not the computations, we're not doing that, but the process that you would use via software. Okay, so I have my data in L1, L2. L1 is the women, L2 is the men. What did you say? L1 is the women, L2 is the men. And with that data in there, we can just go to stat, oops, over to tests. And the z-test and the t-test is what we did in chapter 9, z for 9.2, t for 9.3. So we could have used those if we'd known about it, and I didn't want you to know about it. I want you to do things by hand first and get a feel for it. But now that our computations are out of hand, we definitely want to rely on using the calculator to do our work for us. We're doing 2 sample t-tests. There's 2 samples of men and women, and because we don't have sigmas, the population standard deviations, and we're going to use S, the sample standard deviations, as estimates of those. You deal with t-tests whenever using S to estimate sigma, an unknown sigma. Anyway, you click that, and you can either input the raw data, which I put in L1, L2 already, or stats, and I'll address that in a little bit, but we're using the raw data that's in L1. Group 1 is in L1, Group 2 is in L2. Frequencies, these default to 1 and leave it as 1. We don't have frequency tables. We have actual individual data points in our table. You can choose a two-tailed test here, a left-tailed test, a right-tailed test. And here's where it's important to remember which one's Group 1 and which one's Group 2. Women were Group 1, and we were looking to test if women had a higher IQ, so it'd be this one over here. Okay, so you highlight that one. You had the choice between pooled or non-pooled. I said we default to pooled. Well, yeah, let's just go with pooled. And then calculate. And it does all the computations that I had on that small board for you. Pulls the standard deviations and gets you your t of 0.329. And more importantly, the p-value, 0.376 if I round it. And that led us to the conclusion that we were not going to reject the null and that we did not feel there was a statistically significant difference between the IQs of men and women. So that's the result of that. Okay, so that's a 2 independent sample test. I'm going to mention that if you didn't, a lot of times you have way more than 4 women and 5 men. When you're trying to do a test like this, you have possibly 50 of each or hundreds of each, in which case typing that in manually into L1, L2 is not going to be practical. So all these tests have the option of not working with the actual data, but instead just looking at the summary statistics for each group. And when I click this, it gives me a different menu and is prompting me for X bar 1, the average IQ of our sample of women. This is a rounded figure, so I'm using rounded figures here, approximations based on something that I did before I even started this lecture, 13.77. And N1 is the number of women was 4. And that saves me the trouble working with the raw data and typing all that in. This is all they need to do it. The mean, standard deviation, and the sample size for each of the 2 groups. X2, 105.2. Standard deviation was 13.85, rounded to 2 places, but that's not exact. And I had 5 men. So N2 was 5. Okay, oh, it does still make me choose this. It makes me choose if it's pulled or not, and then calculate. And it should, in theory, it will produce the same results, but because I had to round a lot of those X bars and S's, it's a little bit off from there. It's one of those things where if you round it differently or you're using rounded figures, it doesn't do it precisely. The original with the raw data was more precise because it didn't do any rounding. But that's it. That's how you can use your calculator to do this type of test. But the main thing I want you to understand is how that test worked, the p-value. When the difference was big, if the difference between the men and women were big, we'd have a small p-value. But we didn't. We had a relatively large p-value. And this is the software we're going to use, StatCrunch. It's often used by stats instructors at this level because it's a cheap, it used to be free and then they started charging $15 per semester roughly, but it's still the cheapest thing we could use. There's more professional software, statistical software that runs to like hundreds of dollars. We definitely don't want you buying that. So this is a really basic suite of functionality in statistical software, and it can do the things we need to do. And here I have my women and my men as usual, and a lot of our labs is just getting used to playing around and figuring out where things are, how to load data, but more importantly, we could graph some bar plots, pie charts, some histograms, stem and leaf, which I don't really do in the labs at least, box plots, things that you remember from chapter 3. I had a couple of labs that we just skipped because of the situation. Stat, you can do summary statistics. That's like one var stats, various things. Confidence intervals somewhere. I'm not even bothered. But anyway, t-stats is where we would go. I would show you that you're going to do a 2-sample test. And like the other one, you could do with data or with summary. And with summary would be having to enter x1, x bar 1, x bar 2, s1 like we did the last time. But since I put the raw data into my spreadsheet here, we're going to work with data. And a lot of times you have multiple columns and you need to specify which one is your group 1. It's in var, this column labeled var1. I'd specify var variable 2. The where thing is for filtering, which you would have learned a little bit of that in a lab, but it's not a big deal. Your hypotheses tests, the null. Now they wrote it a little bit differently, and here's where you do have to adapt to. Sometimes they don't look at mu1 is equal to mu2. They look at the difference between the IQ of women minus the IQ of men. And our null is that they're the same, meaning that when you subtract them, you get 0. So our null is that the difference between them is 0, meaning no difference. Now, the alternative is that women have a higher IQ than men. I'm not saying that's true, but that was what we were testing. So if women were greater than men and you subtract in this order, you would get a positive difference. So you actually have to be real careful about which way you're subtracting this. Confidence, I mentioned that they can do confidence intervals for hypothesis tests instead of p-values, but now we're going to skip that. It's 5%, but we don't even need that, because what we're doing is we're going to choose the various ways of doing tests, and there's many of them, and we want to just do a summary and hit compute. And it does roughly the same thing the calculator did, and that I also did on the board. Right here is your main thing. T value right there, the T statistic, and its P value. And that's it. And you would get used to doing this. And if you had to work on more professional software for some company, you just have to play around with it and get a feel for how to do it. But I guarantee you it can do this test and produce this exact same results. It's just doing the same computations. It's more just how they've set up their menus and where things are, and you'd get used to doing that kind of thing. Okay, but anyway, that's what we would have used for our lab, StatCrunch right there. Next, I'm going to backtrack, like I said, to do 11.1 because it'll be easier to understand once you've seen the independent samples. So here we're talking about what are called paired samples. The definition means there's a natural pairing between the data from one sample and the other sample, between the two samples. I'll just go straight to an example. We're going to test if a particular diet, a ketogenic diet, which I think is low carbs, but don't quote me on that, promotes weight loss. And how would you test that? You would take a bunch of people and weigh them before they were put on the diet. You put them on the diet for however many weeks, and you start weighing them after. And if it works, you should see some evidence of weight loss. Now, it's random. So, I mean, these are random type of people with random habits, and they may or may not stick to the diet or whatever. But if they do, some might actually gain weight. But in theory, if this diet works, most should lose weight. And you're going to be looking at that difference between them. And you get a difference, to be clear. And it's important you keep track of group 1 and group 2. I should have labeled it. But the befores I'm going to call group 1. The afters I'm going to call group 2, just because that's the order we put it in the tables. But again, you could switch them, but you just have to be really careful. And you have to note that difference is computed by doing the after minus the before. That's how you do a change in something. You do the final value minus initial. And And let me just double check that, because again, it can be tricky and you do have to keep track of how you're computing this difference. Are you doing mu1 minus mu2 or mu2 minus mu1? To get that loss of 5 pounds, I'm doing 162 minus 167, and I get a -5, indicating a change of -5 pounds. That's a correct way to do it, or that's a conventional way to do it. All right. Now, going back to our notion of a hypothesis test, our null is always that things don't work, things stay steady, and we would assume for our null that the diet does not actually do anything. So our null is that the before weights on average will be equal to the weights after, because we assume the diet won't work unless we have evidence that it does, and then we can go and promote this diet and publish books. But until we have evidence, we should assume that it doesn't work. And our alternative will be that it does work. We're looking for evidence of the alternative that it does work. And there's a symbol here, and I need to be careful about which way it goes. So I need to be clear about which one's the before. My mu1 is the befores, and my mu2s are the afters. And if this diet works, then the afters should be lower than the weight befores. So we're looking for that direction. And even though there's two samples here, the sample of befores and the sample of afters, they are paired up. Unlike the men and the women, I mentioned they were not related to each other or married to each other. It was 4 women and 5 men. They didn't have the correct numbers, or the same numbers. And so there was no natural pairing of the men and the women. I mentioned they probably never even met each other. These two samples do have a natural pairing, because that's Bob's before weight and that's Bob's after weight. And we can't mix these up and reorder one column, because then it messes it up, because that 167 goes with that 162. It's the before and after weight of a single subject. 138 pairs up naturally with 140, because that is the weight of a single person before the diet and after the diet, and so on. So they're all paired up, and you should have the same numbers of data points each if it is paired in this way. And so that's one of the things you do in a stats course when you deal with a chapter like this, is make sure you know when the samples are independent, like the men and women and their IQs, or if they're paired, like the befores and afters of this situation. And when you are dealing with a paired one, as we've decided, you don't actually work with the two samples. I mean, you could, but instead, the standard way to do this is to look at the difference and treat it as a one variable test on the difference. So I did 162 minus 167, -5, and so on, and you can see a lot of weight loss. So this person did not gain or lose, that person gained. On average, so D bar, and then you start using D for difference, and D bar for the average difference of your sample, and it's an average of -2.75 pounds. So that's a loss of 2.75 pounds on average for these subjects. Is that enough to conclude the diet works? It depends. We need strong evidence of that. It can't just be a few pounds, it can't be like just a half a pound. Is 2.75 pound loss enough to conclude that the diet works? Well, you got to do a hypothesis test at the 5% significance level. As mentioned, we don't look at X1 bar or X2 bar. In this situation where they're paired, we look at the difference. And this is your standard t-test that you actually did in 9.3. Is a difference different enough from 0? And you do the standard deviation divided by square root of n. That's, they use S for the subscript of D bar to standard deviations of those differences. So you plug that into a column and get the standard deviation of that. Now, that means, since we're looking at just a difference and not the individual averages of the befores and afters, you often need to reinterpret your null and alternative as something related to D. And so here's where you have to spend a little time making sure you have things subtracted in the correct order. The way I've done the difference, and you could do it differently, you could have done the before minus after, but that doesn't really make sense in the context of what we're thinking. To get the correct sign of this for negative change for weight loss and a positive change for weight gain, you do the after minus the before. And so the difference is mu2 minus mu1, after minus before, and if they're equal, that should be 0. So your null if that d is equal to 0. And your alternative will have the same symbol, it's the same number, but a different symbol. And I don't know what it's going to be yet, so I'm going to have to work it out carefully. I'm going to start, and this is how you work it out sometimes on some scratch paper. I want to get the after minus the before, that's the way I'm doing my difference. So I want to get mu2 minus mu1, which means I got to subtract mu1 from both sides. Or let me put it this way. I don't want to do it like that. I'm doing the same thing, but I'm going to write it on the side here. I would subtract mu1 like that. Which tells me that this is just mu2 minus mu1. This is going to be 0. And my inequality here, that I started from there, is going that way. This is my difference, so I'm computing over there after minus before. And so that's what my alternative hypothesis is. Mu1 being greater than mu2 means the difference as computed over there in that order will be less than 0. And no, this inequality is the same as that. The mouth is eating the 0, right? Okay. Can't really get into inequalities right now, but they're equivalent. And so you'd be looking for default, you know that the difference is 0, and you're looking for evidence that it's significantly less than 0. Take that D bar, take the SD bar, fit in right. So you need to also get the standard deviation of that, which I didn't get you, but I'm also not doing it by hand anyway. I'm going to do it on the calculator, and then you would get a p-value and whatnot. All right, I'm going to do it on my calculator, but let me just spit out the p-value and draw our conclusion. Our p-value in this case would be 0.027, and that is less than the significance level of 0.05. What's your conclusion? And I didn't write the significance level, but again, we're going to go with what everybody does in real life. 5% is your standard convention, and our p-value is less than that. Small p-value is evidence that there is a difference. So we are rejecting the null. Our conclusion is therefore the alternative, and so we think the befores are greater than the afters, meaning we think there's a difference. So our conclusion, there's evidence that the diet works. There was a statistically significant difference between the weights before and the weights after the diet. Okay, and that's our conclusion. I'm going to go ahead and just produce this p-value on the calculator real quick. But again, we're not doing the computations to get there. We're just going to have the calculator and the software just spit it out. We'd put the befores and afters and make sure we do the difference in the correct order. So I'm going to go to L3. So I'm going to just compute the differences by doing formulas that we've done. I want to do the final weight minus initial weight. We'll get you the change and the correct sign. Negatives for weight loss, positives for weight gain. So in L3 column header, I'm going to do L2 minus L1. And there, it's a weight, a loss of 5 pounds, gain of 2 pounds, and so on. And this is again the column we're working with, and it's a one variable test now, testing on the difference. I'm going to go to stat, over to tests, t-test, and we're going to use data, not stats. 0 is our null, that the difference is 0. I mentioned that. And our list, I had already changed this, so you'd have to change this to L3, not L1, not L2. We're looking at that difference that we put in column 3. So you make sure you just do this t-test on L3. And I already said this, so it's already said, but you'd have to make sure you're looking at this. You want your difference, the variable in question in L3, to be less than this default value of 0. We want negative change. And calculate. And that's the t, did I write the t-score? I don't remember the t-score or not, but again, the important thing, the p-value 0.027, that indicates at the 5% significance level that there was a difference, that these on average are significantly below 0, meaning there is a statistically significant change in weight or weight loss for these people on this diet. All right. Okay, 11.3, however, is the one that I want to spend more time with. And so I kind of rushed through those others, and I'm going to spend a little more time on this one. But whatever I talk about here does relate to those others, you'll see. But this is the one I can relate better to things you might see that's pertinent to today and the situation we're in. But we're going to keep it into a completely fictional example of testing if jelly beans are linked to acne. And what we would do to do that, and we're going to do different flavors. So I'm going to do purple jelly beans first, and what we would do is we would look at a bunch of people a random selection of people that eat purple jelly beans, and a random selection of people that don't eat any jelly beans. And our assumption is that jelly beans are fine, and we would not expect the proportions of acne, the rates of acne with one group to be any different from the other. We expect them to be the same. And our alternative, what we're looking for to see if they're linked, see if purple jelly beans might be causing acne or linked to increased rate of acne. And here's where we do have to be conscious of what we're trying to improve and which direction the inequality is. So we're supposing that, or we're looking for evidence that purple jelly bean eaters will have higher rates of acne than people that don't eat jelly beans. So that'll make this P1 greater than P2, and we would run some tests on this. So what we need is, what we need is to do this. Now again, we're not actually doing it. It's more complicated than we would want to do by hand, so we're just going to use software. The TI calculator will do it just fine. But it's a z-score, it's a z-statistic that you get by doing the difference between the two proportions, or actually we're going to compute it from this results. You divide by the standard error, a term that I used in the past that said we don't really emphasize it in this course, but it is like a standard deviation of the sampling distribution that accounts for the variation, how much variation we're expecting. It's ugly, yeah. They get ugly for these types of tests. You need to do p hat subscript p, which means the pooled proportion, times 1 minus p pooled proportion, which is like a q, 1 over n1 plus 1 over n2, and that pool proportion is something you have to compute separately, or yeah, pretty much separately, by essentially combining all these people in both samples. You take the 100 and 200 and get 300, count up the total acne people, and get a single proportion that's pooled by combining these. That's what that is. But who cares, because the software does that for us. We'll just get an idea of the general gist of what's happening. And here we want to get a p proportion. And I've kept it nice round numbers, but you're not likely to have exactly 100 and exactly 200 in your sample size. But what we get is 28% of group 1 suffers from acne or got acne. And they're the ones who are eating purple jelly beans. We look at P2, the non-jelly bean eaters, and it's 42 divided by 200. We get a p hat there. Oh, sorry, p hat's actually sample versus population. That is technically relevant. That's going to be 21%, 0.21% of that group suffers acne. And initially, you know, this is higher, 20% versus 21%, but is it different enough? There's always randomness, and it could just be a result of the random variation in sampling. The way we would do that is to actually work out a p-value, well, a test statistic first, then off of that the p-value, and compare it to your standard 5% significance level. Oh, I'm going to do it on the screen anyway. But anyway, when we do it, or when I go over there and do it, you're going to get a p-value, well, let me see, you're going to get a z of 1.352. And more importantly, a p-value, you could go from there and use standard normal distribution to get a p-value of 0.088. Is that sufficient evidence that purple jelly beans are linked to acne? That purple jelly bean eaters have a higher rate of acne? Nope, it's not quite below the cutoff. There's an 8% chance that this is just a random occurrence. Though that may seem small, it is not small enough. We are not rejecting. It's not sufficient evidence for us to worry about purple jelly beans, and our conclusion is purple jelly beans are fine. I'll say safe. And they would actually never say that. They would just say there's no evidence that purple jelly beans are linked to acne. Let me go ahead and do this on my calculator real quick and show you it's a real simple process. We're going to go stat over to tests. And here we're doing a two-proportion z-test because we're looking at two different proportions and comparing them. This one doesn't take data, it takes the actual counts, and it'll do the computations for us. So x1 is the number that suffered from acne in group 1, it was 28. And 1 is a number of subjects in group 1, so it's 28 out of 100 in that group. That's the purple jelly bean eaters. And then we have 42 out of 200 for the non-jelly bean people. Here you have a choice of looking at P1 is not equal to, you're looking for evidence, the alternative hypothesis, that P1 is not equal to, less than P2, or greater than. I was very careful to note that we were looking for evidence that purple jelly beans are linked to acne, so we would see P1 being significantly greater than P2. Enter, and then go on to calculate. Okay, and then I get 1.351, must have been a rounding error. I had 1.352 on the board, but my p-value, I mean, no little rounding errors, but my p-value is 0.088, and we did not reject based on that, but that's how you would do it on here. It did all those computations that I had on the little board internally, and we don't have to worry about it. We just need to be able to interpret p-values at this stage. All right, following up with this, let's say we were going to test a different flavor of jelly beans. Let's say we tested a bunch of flavors of jelly beans, and here we're going to do our second one. Green jelly beans this time. We're going to look at a sample of green jelly bean eaters and another sample of no jelly bean eaters. And I'm going to keep it still relatively simple and I'm going to say 42 of the 200 non-jelly bean eaters got acne. I'm going to change it up here, and let's say we have 34 out of 100 green jelly bean eaters suffer from acne. And we work the same test again. I'm reusing that because it's the same test. We're looking for evidence that this has a higher rate of acne, significantly higher. And this time our P1 ends up being 0.34, 34%. So that is higher than the purple jelly beans. So we're more likely to reject. Anyway, P2 is still going to be 21. And I would use my calculator to get the calculator to do all of that. But the main thing is getting a p-value. I'll write the z as well. Z is going to be 2.442, meaning further out along the tail, meaning you're going to get a smaller p-value. My p-value this time is 0.007, less than 1%. There's a less than 1% chance that this high rate of acne is just the result of random variation. Our conclusion will be, because we're going to be rejecting the no, at the 5% significance level, we are going to be rejecting, and that means our conclusion is people who eat green jelly beans do have a higher rate of acne, meaning green jelly beans are of a concern. Now, there's a possibility that it was just random variation. I do want to note that this 0.05, this 5% significance level, which I mentioned is the convention that most studies use, that's equal to 1 out of 20. Oh, sorry, let me finish up the statement. Green jelly beans, bad? I'm trying to use just layman terms, but I'm going to put a question mark because we're not 100% sure, and I'm going to talk about what we would do at this stage regarding green jelly beans. Short spoiler, we would just recommend further study of green jelly beans. We wouldn't necessarily ban it or have everybody panic over it or recall it from the stores. We would just probably do another study to confirm this result if it is, and see if it is indeed linked to acne. Anyway, I'm going to do a thing where I refer to the fact that 5% cutoff is 1 out of 20. An example was based on this comic, which is fictional, so the whole thing is fictional, but it does illustrate p-values. This is a comic that does a lot of scientific references and statistical jokes and things like that. Anyway, they're going to test jelly beans cause acne and yada yada. They refer to p-values in this, so this is interesting. And they're going to test 20 flavors of jelly beans, which is important, referring to the 1 out of 20. Right here, they did purple like we did, and they got a p-value greater than 0.05, meaning they did not reject, and therefore purple is deemed safe. Brown, we didn't do that, but they're saying you get another p-value that's greater than 0.05, brown is safe. Pink is safe, blue is safe, teal is safe. Salmon is safe, red is safe, turquoise safe, magenta safe, yellow safe. Don't worry, this is going somewhere. Gray safe, tan safe, cyan safe, green. And green right here, the first time you have a p-value less than 0.05 like we did. And in that situation, you would reject the no. You would reject the no that the proportions of acne are the same, and you would go with the alternative that green jelly bean eaters do have higher rates of acne. it's a statistically significant result. And somebody off screen says, whoa. They continue on. Mauve is safe. Beige is safe. Lilac is safe. Black is safe. Peach is safe. Orange is safe. So out of the 20, one came up with a p-value that was less than 0.05. So there was a 1 out of 20 chance that this would be a random result. And our conclusion, based on it that being a quote-unquote small probability, is that no, there's something going on with green jelly beans. Okay, so here's a simplified version of it. The idea is I'm going to do the distribution around P2. The non-jelly bean eaters was 21%. And we first tested purple jelly bean eaters, and we found that P1 was 0.28. Okay, and so the idea is that that proportion of people that had acne, regardless of what jelly beans they eat, is random. If the rate of acne amongst the general population is 21%, you take a random sample of anybody who eats anything, you'll get random results. You'll never get 20% exactly. You might get slightly below, slightly above. So you get this random result, this random proportion of people getting acne who happen to be eating a certain food, like purple jelly beans. But that wasn't significant. That difference wasn't enough for us to conclude that it was dangerous. It just meant that we assumed it was just random. And so if you test another flavor like mauve or brown or red, cyan, purple, which was 0.34, some other color, yada yada. Well, I should actually put more around here. Most of them will be closer to 0.21. You'll have some further on the outside. But they'll be all over the place. All 20 flavors of jelly beans will result in different proportions of getting acne. And it's just random. Presumably, I don't want to say presumably, but let's assume all those jelly beans flavors were safe. And we tested 20 of them. Now, there's a specific cutoff that we're using in tests where we decide what we consider significant and possibly linked to acne, and what we say is safe and not linked to acne at all. And that cutoff is a 5% significance level. We're looking for something further out on the table, that's in the rejection region, the 5% rejection region. I did use that term, not a lot, but in my first introduction into the concept of using p-values to draw your conclusions. And which means, not purple, this is green jelly beans. Because that happened to fall in that rejection region, that was flagged as possibly linked to acne. Yeah. And we don't say possibly, we just say there was a statistically significant difference between people that don't eat jelly beans and people that eat green. All the others were safe, but that one turned up as a reject the null hypothesis. But it's probably just random. You can see how it works. It's going to be random, mostly around here, but the 5% means there's a 1 out of 20 chance that you might get something in here by random chance. And so this is probably, even though we flag it as something to look into, if green jelly beans are safe, if all jelly beans are safe, then this is the correct conclusion for all of them, because we did not reject for all of these and said these were all safe. And this would have just been a type 1 error. We rejected a null, but it was true all along, meaning that jelly bean would happen to be safe. Okay, so that happens. When you test a bunch of things, things pop up as being statistically significant, possibly linked to cancer, possibly linked to weight gain, various other health problems. And so the media does not really properly contextualize a result like that, like the green jelly bean result, where the conclusion was it was statistically significant, and the conclusion was that it does have a higher rate of acne. The media will just grab that headline and run clickbait articles because they just want clicks, and they'll blow it out of proportion, even though it's probably just a type 1 error. And that's a problem, is people don't know how to filter these studies and look at the totality, and they'll focus on one study that grabs headlines like this green jelly being linked to acne. So that's, again, fictional situation, but this is a real life problem for getting out scientific information to the public. And the public themselves oftentimes does not know how to process information, so there's a phenomena called single study syndrome, which means people will focus on a single study. They'll read about a single study, and that will inform their entire opinion about something, even though there are contradictory studies, even though there are many other studies that have a different conclusion. I think this is a good phrasing of it. I'm not going to click on these and read it or anything, but single study syndrome, there's enough articles that it is a problem, and it's clutching at convenient confirmation is the way this phrased it here. So they will seize on the one thing that confirms their beliefs, and they won't let go of it, and you can't really convince them otherwise, even if you show them the other studies that contradict it. It's important to understand the dangers of single study syndrome and not get fixated or just jump on one study that you may have seen in the media. An example of this real life, unlike the fictional example with the jelly beans, is, well, masks. So they've been looking at it. Not all studies related to this are COVID specifics. They did a lot of studies with MERS and SARS, and they found that the overwhelming evidence is that masks are effective. So the CDC compiled a lot of these to try to convince people to wear their masks. And establish that it does work. It does reduce the spread of the infection. But if you go online and on Facebook and various things, you might encounter somebody claiming that there's a study that proves that masks don't work. And so So what you need to look at is the balance of the evidence, the totality of all these studies versus the one study they're citing, the Danish study. And you can go on Google and you can see fact checkers try to refute it and try to stop the misinformation, saying it does not prove that wearing masks is ineffective. But I want to look at this specific study closely, just to illustrate some things. And is this in our window? Yeah, okay. Yada yada yada. So this is a typical study on the effectiveness of masks. They would compare two proportions. Two samples, and the proportions, just like with the jelly beans, they had a certain number of participants. Over here is basically it, the results. The ones that wore masks had a 1.8% rate of getting SARS. Again, not COVID. Is it? No, this is COVID, yeah. Okay, anyway. The control group, the ones that did not have masks, had a rate of 2.1%. So it did have this very slight reduction. But according to the methods of this test, the 5% significance level, when they did the same test that we just did, this was deemed not statistically significant. It had a p-value of right here, 0.33. So these p-values come up in real-life studies, and they do inform our decisions. But again, this one study does not outweigh the multitude of other studies that confirm that masks do work. So the consensus is that masks do work because there's 20-something studies versus the one. So that's all the ones that confirm it. And so you have a situation that I can illustrate in a very simplified version of it. To illustrate, ultimately what we're doing with that test is we start with the null hypothesis that the proportion of people getting COVID is the same, people wearing masks get COVID at the same rate as people who don't wear masks. And until you have evidence otherwise, and you look at, at the 5% significance level, to reject the null and say that you do have a reduction in the rate of the spread. And based on that particular study, they said 2.1% got it who weren't wearing masks. And their sample that did wear masks, of the Danish sample that did have masks, it was 1.8%. So it was lower, and all the other studies had results that were lower. So there are other studies that have way over here, much bigger reductions of less than 1% or so on. So they're all over here, literally 19 studies. And based on our cutoff though, anyway, the totality of the evidence is it does work. You are getting a reduction in COVID spread, which is why they recommend it. But strictly speaking, the 5% significance level, alright, that's your 0.05. These 19 studies in that one folder were all rejecting the null. Rejecting that. There was sufficient evidence that masks do result in a lower rate or a lower rate of spread of the virus. But you have this one study that didn't quite make the cut. Again, notice that it was a lower percentage than the people not wearing masks, but it wasn't low enough to make that 5% cutoff. Again, clearly masks work if you look at the totality, but if you are fixated on that one study or you wanted to confirm your beliefs and you're just anti-mask, you're going to point to that one study, ignore all of this, and you're going to basically grapple on to what is ultimately a type 2 error, where the null was false all along, but you did not reject and you said it was not statistically significant and therefore you object to wearing masks. Anyway, that's an issue, single study syndrome, but p-values are relevant and no single p-value on any single study will result in a scientific consensus. It's multiple studies that they gather and confirming or corroborating previous results leads to scientists getting an idea of what's working and what's not. Anyway, that's what you're going to see on Facebook and YouTube comments and whatever's going on, and Twitter probably, but just be aware that that's how hypotheses tests work in real life. Alright, and anyway, you're not going to be tested on that or anything.